much of this as we can in 15, 20 minutes. Alright, the standard, and if you can meet that standard, you would get a 3, is I can graph linear equations and identify the slope and the intercepts. The extension to that, which we will practice, is I can describe in words what the slope and intercepts mean in context of the problem. Alright, so in this unit we have a heavy focus on graphing. Sometimes the question is asked, why do we need to graph? Can't I just solve the problem? This question is usually asked for one of two reasons. Number one, the student doesn't know how to graph, and therefore it's easier to pretend it isn't there, which is understandable. Or two, they hate art, which I was obviously just kidding about that. But seriously, why do we have to graph? It's a big part of the rest of your math career, so you better understand why you're doing what you're doing so that when you do it, you find it a little bit worthwhile. Okay, so graphing. Graphing gives us a picture of what is happening algebraically. Or you can say maybe even mathematically. Excuse me. Because when we get to statistics later on in the year, it's not really algebraically that we're drawing pictures, but we're still drawing a picture of what's happening mathematically. It allows us to extend excuse me. Alright, allows us to extend the algebra concept out as far as we want it to go and find values at any x value. And these values that you find are your y values. Okay, so basically it takes maybe the small picture that we have, extends it out, towards infinity, and then let's say I just have data between, I don't know, -2 and 10, and I want to see what the value would be when x is 100. Well, instead of punching out 100 more x values to get to my y value, I can make a function, predict the future, and then plug in my x to get my y for an x value that's way in the future. Graphs make it much easier to assess what's going on with a function in a big picture sort of way than just having numbers with variables written down in front of us. So, on that note, we're going to start with graphing linear functions. A good place to start since linears are our first algebra function. But before we do that, we have to quick review on some terms. Okay, so function, this is a dependent relationship between two variables. Every input has only one output, meaning this is a situation where you can plug in 2 and get out, let's say, 4 every single time. Does not matter how many times you plug in 2, you always get the same y value out. Alright, domain, these are my x values that work in the function. There will be functions that we look at where some x values are excluded because of something that's going on with the function, and we'll get to that. Range, these are y values that exist in the function. Now the difference between this terminology, the working and the existing, is that x values that work, that's something that when you plug it in, it actually can be punched out. Y values that exist, that means like these are dependent on what the x values are, so that's why the word is exist, not work, because you don't plug y values in necessarily. And so maybe we need to put that here. These are the independent values, domain is, and range are the dependent values. Okay, when I say intercepts, I want you to say or to think these are the places your function connects with the axes. So, where y equals 0 and where x equals 0. basically the spots on the graph that will connect or intersect the x and y axis. Usually, well, and I'll say this kind of over and over again, the most important points for any type of function that we have are like max or min points, if those exist in the function, and then intercepts. Usually the intercepts and the max and min points, if we're looking at a real life situation, they're the ones that tell us the most information about what's going on in that situation. So those are what I call the most important points, the intercepts and the max and min points. Okay, and then slope. Slope can be thought of as rise over run. It can also be thought of as the change in the change in y over the change in x. It can also be thought of as a rate of change. We'll review how to find slope today. Okay, these are all key terms that we will use all semester long. I want you to know them. You will not have to define on a summative assessment what these terms are, but you better know what they mean if I refer to them. Smiley face. So basically, like when I say domain, I need you to be able to know what that is. If I say slope, I need you to be able to know what that is. So these are important things that you have to know, but not necessarily something that I'm going to test you on. Okay, flip the page. On to the main event. How do we graph linear functions? Well, maybe let's extend that out a little bit. How do we graph any algebraic function? With any algebraic function that we deal with, you can always graph by making a table of values. Basically saying plugging in a bunch of x's, finding the y's, and plotting points. If we did that every time, it would be tedious, annoying, frustrating, etc. So the other way we have to graph functions is usually I teach you a shortcut or a method depending on the function that makes it quicker, easier, and usually more accurate. So graphing linear functions is where we are going to start. First step to graphing linear function. So again, let me clarify. You can graph anything by using a table of values. If you have enough points, you know the pattern, and you can connect them and get a good, accurate graph. However, sometimes we'd have to find a bunch of points, and then it's just tedious to plot all those points. So when I give you steps to graphing something, this is like my shortcut or my quicker method to doing it. Okay? So steps to graphing linear functions. We're going to rewrite function so it is in y equals mx plus b form. As someone reminded us yesterday, that's called the slope-intercept form. Okay. So the first step, get y by itself. Get it in y equals mx plus b form. Next thing that we are going to do is we're going to identify the slope, which is your m value, and the y-intercept, which is your b value. The reason the y-intercept, we can plot it, is because the y-intercept would happen, and remember intercept means where it's going to connect with the y-axis. That would be where x is 0. So if we were to plug 0 in for any x here, it's going to knock off that middle term, and you're just left with y equals b. So that's why that always happens, that the y-intercept can be the b value. Okay, and then you start by plotting the y-intercept on the y-axis, and then use the slope to make one more point. Graph the line. Okay, so let's do an example of this. Let's start with 2x minus 3y equals 10. Okay, so the first thing that we're going to do here is we are going to rewrite the function so it's in y equals mx plus b form. I'm going to isolate or get y by itself to to do that, I need to subtract 2x from both sides. So I get negative 3y equals negative 2x plus 10. Now, the reason I put the negative 2x first is so that I get it into that y equals mx plus b form. So I want my x term first. We're going to divide everything by negative 3. So we get y equals positive 2/3 x minus 10/3. Now this is how I want you to leave it when you're solving for y equals mx plus b form. But then we're going to identify the slope and the y-intercept. The slope is the number attached to your x term. This means you're going to go up 2 and to the right 3. That's the increase of the line, or the rate of change. For every 3 you go forward, your line rises 2 units. And then for b, my b is negative 10/3. Now, as a y-intercept, you could write it as 0, negative 10/3, because technically this is a point in order to pair, but it's the point that happens when your x is 0. Okay, oops, which you can't even see that. Sorry. Alright, so we're going to plot this negative 10/3. Now, negative 10/3 is a decimal. It's like 3.33 or something like that. And it's negative, so we're going to go down 1, 2, 3, and a little bit. There's my point 0, negative 10/3. And then from that point, I'm going to use my slope to come up with another point. So I'm going to go up 2 over 3, 1, 2, 3. And then I don't have a ruler on me, but I do expect you to draw your lines to cover the whole graph. It will matter later when we have to draw more than one line on a page that we're able to see the whole picture. So don't just draw a little stubby line. Make sure you cover the whole thing. And that's it. That's the basic standard that you can do those steps. So let's go ahead and practice one more. Okay. Let's go with 4y plus 2x equals 5. Okay, so same thing. We're going to get y by itself. I'm going to subtract 2x from both sides and get 4y equals negative 2x plus 5. And then divide everything by 4. So you get y equals, now negative 2 over 4. If you can reduce that, do it. So we get negative 1/2 x. And then plus 5/4. Okay, let's identify the slope. The slope is negative 1/2, which means I'm going to go down 1 for every 2 I go forward. And then my b value is 5/4, and as in order to pair, I could write it as 0 5/4. And to graph, we're going to start by graphing that y-intercept. So we have 0, 1, and 1/4. And then from that point, we're going to go down 1 and over 2. Make another point, and then draw in your line as best you can. Now, notice with the line, it tells me some information in general about the graph. It means as I move left to right in this situation, my line is going to continually fall at that rate of negative 1/2. And so whatever this represents, that means the situation is decreasing. Let's say it's a company's stock. Well, if this was the pattern over a period of time, we could assume that it's going to keep going in that direction, and therefore we know it to keep decreasing because of the way the graph looks. Okay, let me just check the time here. Alright. Yeah, I think I'll hold you off there. We'll do this real-life extension problem together tomorrow. Yeah, that's your first homework video. I think that's where we'll stop.